We just started recording, so perfect. Hello, everybody. Welcome to the Graduate Online Combinatorics Colloquium. Today, I'm delighted to introduce Eric Nathan Stucky, who's not only one of my colleagues at the University of Minnesota, but also my academic brother. We have the same advisor. He's going to talk about strange expectations for simultaneous cores, but before he does that, I want to remind us all of the GOCC's guiding principles. These are on our website under our community statement, but I'm just going to remind you what they are before we start, which is that 1, we're all learning, 2, everyone has something to contribute, and 3, no one has all the answers. There's more detail and it's more eloquently explained in our community statement on our website. But briefly, I just want to remind everyone to ask questions either through the chat, which Alex and I will be monitoring, or you can unmute yourself and ask Eric directly if you're feeling brave. And then, as always, we'll have time for questions at the end of the talk, both a recorded part and then an unrecorded question session if you have questions you don't want to ask on record. Okay, great. Take it away, Eric.
Thank you for the introduction. So I'm going to be talking about strange expectations for simultaneous cores, and this is joint work that is upcoming with Nathan Williams and Marco Thiel. So in particular, these two have already written a paper called Strange Expectations, and so we have extended it in a certain way that I'll say a little bit about toward the end of the talk. Oops. Be good to do this. But I will follow the traditional math talk outline of explaining the words in the title in reverse order. So we'll start with cores. I'll say what it means to be a simultaneous core. There will be this interlude about Ehrhart theory, also an interlude about root systems. And then at the end, we'll say something about expectations and what's strange about them. So the whole talk, I should mention, is going to be sort of doubled in the sense we'll talk about cores and then we'll talk about cores for root systems, simultaneous cores and simultaneous cores for root systems and so on. And if at the end of the day, all you come out of the talk with is the parts without the root systems, then it's an expository talk instead of a research talk. But I think the story there is still very beautiful and it's worth recognizing that mathematics, even if we don't sort of say it in the most general possible way. So let's talk about cores. So these are fundamentally partitions. So a partition can be thought of in a lot of ways, but the most basic way is you say it's a sequence of integers that is non-increasing. And the usual way of representing this is through this picture called a Young diagram, where we place the boxes here in French notation. So lower justified and justified on the left. I think that's the left. So there's the Young diagram is going to be useful for us more than just like a visualization technique, because we're going to define these statistics called hook lengths, which is for each cell in the Young diagram, you look at the number of cells to the right of it and above it, and including itself, and you count those up. So in this case, the shaded cell here has hook length 5, and we can fill in hook lengths for all of the others. And we care about this because the notion of a core is a partition such that any of the hook lengths for any of the cells is not divisible by a particular number A. So here we can say that this partition is a 3-core, it's also a 7-core, but it's not a 4-core because not only do we have a box with, or excuse me, a cell with hook length 4, but we also have one with hook length 8, which is also not allowed in these cores. But this is not the only way that we can think about partitions. And so there's a second method of doing it that's going to be useful for this purpose of generalizing to root systems, which is that we can translate this whole story to an abacus diagram. So this translation process works by thinking of starting at positive infinity on the y-axis and ending at positive infinity on the x-axis. And when you get near the origin where the partition is, you're going to trace along the boundary. And every time we go down a step, we're going to place a bead onto this diagram. And every time we go to the right, we're going to skip the position. We're going to place a gap. So we have an infinite string of beads, which is represented by this row of beads at the bottom of the diagram. And then at some point, we move to the right. And so that's the place of our first gap. And then we go down 2, so that's 2 beans. And then we go to the right 2, so that's 2 gaps, and so on. And eventually, we reach the end of the partition, and we just go right forever. And so we're going to end with an infinite string of gaps. So the advantage to thinking about abacus diagrams is that they give us a really immediate visual way of seeing whether or not a partition is an A core. So you can do the calculation from the Young diagram, but it's a little bit tedious. But from the abacus diagram, the condition is simply that all of the beads are as low as possible. So there's never going to be any positions, any bead that comes directly above a gap. We already know that this partition is not a 4-core, and so the fact that in this first column we have that bead that's sort of hanging up there way too high is representing that fact for this partition. But we also know that this thing is a 3-core, and so if we try winding it onto a diagram with only 3 columns, then we do have this flush condition. We end up being all of in each column, it's just a bunch of beads and then a bunch of gaps. So one thing that I sort of snuck under the rug is that abacus diagrams are not unique, right? So there's this question about where do we place the first gap, so because we're taking this infinite sequence, and so do we start in the first column or start in any other column? And the answer is you can do whatever you want, but there are some natural choices. One is to just put it in the first column, but a more subtle one is given by this picture on the right. And this is the one we're going to prefer. And the reason why we like this is because we are able to draw this blue line. And the significance of that blue line is that the number of beads above the line is equal to the number of gaps below the line. So you can see if you try to do that on the left-hand side, it doesn't work. You're either going to have too many beads or too many gaps, and so right, and so the diagram on the left we say is not balanced. The diagram on the right we say is balanced. And it turns out that every partition has a unique balanced diagram. So this can be shown from the cyclolemma or a variation of the cyclolemma, depending on what you call it. So it's similar in techniques to showing that Catalan paths are given, right? That 1/n or 1/2n plus 1 is really the right thing to divide by, if that means anything to you. But when we move from general partitions to specifically A cores, we get a little bit more, we can say a little bit more, which is that since every column goes a bunch of beads and a bunch of gaps, the column is completely determined by where the highest bead is. And therefore, if we know that the diagram is balanced as well, then we have this method of parametrizing these objects, which is that we just record the height of the bead in each column. And then to satisfy the balance condition, we need that the sum of the heights is equal to 0.
I just want to interrupt for a second. We have a question from Dari. It looks like he's outlined a proof of this lemma. I don't know if Dari wants to unmute and mention, or if you want to read the chat or whatever works.
Oh, it's not very important. I'm just confused as to when you need the cycle lemma.
You don't need the cycle lemma. Yeah, what you're saying here looks like it's gonna work. But this is just another. This is just the way that we tend to think, or like that, that me and Nathan and Marco tend to think about it. Are there other questions at this juncture? So this last couple of slides have been an outline of the proof of this statement, which is that the set of A cores is in bijection. This like convert to an Abacus diagram and then record the heights with the type A -1 coroot lattice, which, if this is not a familiar object, you can take the equality in this proposition as a definition. Right? It's just exactly what it needs to be, A tuples that have their sum equal to 0. But we will talk about coroot lattices in general just coming up. So the plan is to generalize the notion of cores and then things beyond that to root systems. So we need to talk about what a root system is. If you've seen these things before, then you should know that every time I say root system, I'm talking about a crystallographic, reduced, and normalized root system. If those words don't mean anything to you, just know that the things that I'm going to be talking about are not the only things that people call root systems. And so if there's some discrepancy with stuff you've heard before, it's probably because of these adjectives that I'm going to omit. But here's the definition. It's not super useful. Don't try to like take this all in. But this second axiom here is really the one that is most useful to understand and really sort of gets at what a root system is supposed to be doing. So I'm gonna say a little bit about this. What we're going to do is we're going to take our set of vectors and we're going to start reflecting them across the hyperplanes defined by other vectors. So as a specific example, we can look in the plane. We can take two vectors, and these were carefully chosen, so this will work out. By applying this orange axiom, what we're going to do is take the hyperplanes, in this case just a line, which is orthogonal to the purple vector here. And we're going to reflect both of the vectors across that line. And so the fact that we have to satisfy this orange axiom means that we have to have these two vectors in our root system as well. And we can keep playing this game. The blue line, the blue vector, this is orthogonal to this blue vertical line. And when we reflect everything through this line, we get a couple more. And because these vectors were carefully chosen, we see that those two original gray vectors here were reflected across the line to each other. And indeed, there's a whole bunch of collapsing that happens more generally. Right? We can take these three lines and everything, you can reflect across them, but you don't get anything new. So this is really what is significant about root systems is that after doing these reflections, in principle, an infinite number of times to get all possible vectors that you could get in this way, you end up only getting a finite number of objects. So root systems have a bunch of things associated with them, and I will sort of keep the technology to a minimum for what we need here, but there's certainly a lot of gadgets that we could talk about. So the first thing is that we're going to cut this root system in half, and this is a completely arbitrary choice, although there are certain choices that are standard. So what we do is we take a hyperplane. It doesn't have to be one of the hyperplanes orthogonal to the roots, but just something that doesn't contain any of the other roots. And then we declare one side to be positive and the other side to be negative. And so in this picture, the colored roots are the positive ones, and the grayed out ones are the negative ones, given by choosing the hyperplane that's sort of like mostly horizontal, but a little bit tilted. And so I've highlighted, there's coloring is a little bit different than we saw on the last slide, because I want to point out some of these features, which is if you draw that dividing hyperplane in there, these two blue roots are closest to that hyperplane and in some sense. So here, like literally, there's the positive roots closest to it are precisely these two blue ones. Generally, you have to be a little bit more sophisticated. And these are called the simple roots. So the magic of these root systems, part of the magic of these root systems, is that any positive root can be written as an integer sum of the simple roots. And moreover, there is a unique root that maximizes the coefficients for every plate. So it shouldn't surprise you that you can get some maximizers, but what is surprising is that it's unique, right? If you have two roots where one is maximizing like the first coefficient and the other is maximizing the second coefficient, then you can find an even higher root, which maximizes both. So there's going to be 4 important integers associated to root systems, and with these features we got on the last slide, we can define 2 of them. So one of them is very straightforward. The rank of the root system is the ambient dimension of the vector space. So in all of the examples we'll see in this talk, it's 2 because we don't really like to draw pictures that are bigger than that. But a more subtle number associated to the root system is this thing called the Coxeter number. So this is given by taking that highest root and writing it in terms of the simple roots. So actually finding those coefficients that maximize those maximal coefficients, sorry. And then we take the coefficients, throw away the simple roots, and just add the numbers together. Add a 1 for good measure, and this thing is what we call Coxeter number. This is the definition that I want you to think of, because we're going to define something called the dual Coxeter number, which has sort of an analogous definition. But for computational purposes, it's useful to keep in mind that the Coxeter number is just count the number of roots and then divide by the rank. So I said that we're going to get to the other 2 much later. I don't think that's true. I think it's going to be in a couple of slides. But in order to talk about them, they're not so interesting in the root system that we just talked about, which is usually called A2. So we're going to have to go to think about a different root system in order to sort of find the interesting story there. So this root system is usually called B2, and it's just the unit vectors in the x direction, in the y direction, and then the sum of those to get you this this collection of 8 vectors. And for each root, so for each vector in the root system, we can talk about this thing called the co-root, which is just a scaled version of the root. So why should you do this? Well, there's really a story here about like dual vector spaces, and it's going to be more involved than we really need to think for our purposes. So we're just going to scale the vectors. What you may notice from this picture is that we have 2 kinds of roots. We have short roots and long roots. So the diagonal pointing ones are longer than the ones that are on the axes. And you may think that like as we go to more and more complicated root systems, we get more and more possibilities, but surprisingly, that doesn't happen. You always have roots that are as short as possible or as long as possible. There's no way to have roots that are sort of in the middle. And something that I smuggled into that list that we breezed over at the very beginning was that the long roots are always going to have length square root of 2. And so you plug that into the definition up there, and you can see that that means that every long root is going to be its own co-root. So when we move from roots to co-roots, we are going to only worry about what happens to the small roots, or excuse me, to the short roots. And then we'll say something about this like at the very, very end, but useful to just like have in the back of your mind that co-roots form a root system sort of morally. Technically, because we've defined a root system to require this normalization, the roots are all too long. So you can just scale them down, and so that the long roots have the appropriate length, or rather the long co-roots have the appropriate length, and that will be an honest root system, which is called the dual root. So applying this story here, you see, let me do that transition again. These are the roots, and if you look at the short roots on the axes, you see that those get longer, and they get longer by a factor of 2. Because the length of the roots is 1, and so that scaling factor is 2. So now for some more gadgets. In particular, we get to talk about these remaining 2 numbers. That scaling ratio, the how much longer a long root is than a short root squared is we're going to call R. And so one significance of R for our purposes is that square root of R is the thing that you need to scale the co-root system by in order to get a root system. Although we'll see sort of more significant features of it later. And I promised that we were going to have this thing called the dual Coxeter number. And this is the definition. You take the highest root. The highest root is always going to be a long root, so you can say the highest co-root. These things are equivalent. And you write them in terms of the simple roots, the co-roots corresponding to the simple roots. So these will generally give you different coefficients than you had before, and the dual Coxeter number is those coefficients plus 1. So here we can see that the purple vector is just the sum of those 2 blue vectors. So each of the di's is 1, and so the dual Coxeter number here is 3. Which, again, if this is a story you have seen things about root systems before, you may notice that the dual Coxeter number of this root system is not the Coxeter number of the dual root system. And so this is somewhat confusing, but generally when we're talking about co-roots or duals in that sense, we'll put little checks here. And so that's why I haven't called this thing H check, because it really isn't, right? It's really some genuinely different object.
So when you say check, is that the like little V that's over some of the variables?
Yeah, thanks.
Okay.
Thanks for clarifying that. So the last thing we are going to need about root systems is the co-root lattice. So a while back, I said that cores were elements of the co-root lattice in type A, and in general, a co-root lattice for a root system is the set of all integer combinations of every co-root. So here I've drawn the root system and the co-root lattice. So that's why the dots don't quite align with the arrows. So we have to scale the roots out in order to get at that, this dot, for instance, on the x-axis here. Right. So this proposition, just restating it, the type A co-root lattices are, have this form, and the set of A cores is in bijection with those elements. And so it makes sense to say that for an arbitrary root system, the set of phi cores is the elements of, or well, the phi cores are the elements of the co-root lattice. This is sort of an annoying thing. You want to say like the phi cores are the co-roots, but that's not true, right? You have to think about this whole infinite collection of objects. They're elements of the co-root lattice. So we're about to shift gears and talk about simultaneous cores. So this is a great time to ask about root system questions.
I guess just going back to that last statement you had about the connection to the A cores, I'm just trying to remember back exactly how that works. So is that saying it's all of the possible young tableau that you don't have, or like the young diagram shapes such that you don't have any hook lengths that are multiples of A, like each of those is an A core, or is it something?
Yeah, that's exactly right.
Okay, so it's, I mean, that's certainly infinite, and then the type AA minus one co-root lattice is also infinite. That's
yeah.
Okay. Yeah, I can believe that. I couldn't prove it for you at the moment, but I could believe that.
Yeah. And this is a property that transitions over to phi cores, right? The co-root lattice is generally an infinite object. And so we expect to have, we do have infinitely many cores for any root system. All right. So I promised that we would not just talk about cores, but talk about simultaneous cores. So this is what a simultaneous core is. It is a partition called an AB core if it's both an A core and a B core. So this is a straightforward definition, but you might reasonably ask why. Originally, cores sort of came up in the context of studying modular representations of the symmetric group, and so it's not so clear that like having two different parameters here is meaningful in that sense. But the reason why we like to think about this, especially in combinatorics, is because of this theorem by Jacqueline Anderson from 2002. So she showed that when A and B are co-prime, the A-B cores are in bijection with the set of rational Catalan paths. right? So briefly, those are like Catalan paths. You're trying to stay above the diagonal in a lattice block, but instead of in a square, you're doing it in a rectangle. We're not going to say anything more about Catalan objects in, well, at least Catalan paths in this talk. But the thing, right, that sort of I want you to take away from this theorem is that, first of all, we know how to count rational Catalan paths. And so we got a count for these simultaneous cores. And secondly, these are objects that are extremely well studied. And so thinking about these simultaneous cores, like there's a very natural sort of reason to want to do that. And then also this maybe sort of back justifies why we might want to think about generalizing in the root system direction, because there are these Coxeter generalizations of Catalan objects, and so we can try to reproduce the same story for these cores. And so that's the plan now. We're going to talk about simultaneous cores for other root systems. And in order to do that, we need to reframe this notion of being a simultaneous core in terms of the type A root system. So that's what we'll do right now. So going back to A2, so that's little a equals 3, and just taking b equals 4, we can plug it into Anderson's formula and see that there are going to be 5 of these objects. And so let's try to find them, right? We can take our bijection and find the 3 cores. All of these things are 3 cores, but find the ones that are also 4 cores. Right? And we know that there should be 5 of them. So where are they? So to draw that picture a little bit more clearly, I'm going to replace all of the dots, the co-root lattice elements, with hexagons, right? Just so that there's like a space for me to put these partitions in. And a few of them, these things get sort of annoying to calculate, which is why I didn't go all the way out to the end. But here's a representative sample, and they might sort of appear scattered around the plane haphazardly. There's definitely a lot of things you can say, but maybe the easiest thing is that they sort of get more complicated as you go out in rings. So like the ones with 1, 2, 4, and 5 boxes are in that first ring, and then more boxes than that sort of exist in the second ring, and you go out further, and these things get more complicated. So where are the 4 cores? Well, they're these. Right? Certainly all of these work, and then for the ones that I calculated, I showed all of the boxes where you have 4s and 8s. So those are obstructions to being a 4 core, and indeed there are 5 of them sort of clustered near the origin. And if we believe the Anderson results, then we shouldn't expect to find any more just sort of out there far away. And if we try doing this for other values of b, we find that things still sort of stay near the origin, and a pattern maybe starts to emerge. It sure looks like all of these cores exist in some kind of triangle. So that is that is something that we're going to sort of latch onto, because this triangle was actually not first realized in the context of cores. It was first observed by Sommers when he was thinking about ideals of a nil radical in some other context. He defined this simplex that we call the Sommers region. And it has some sort of big definition here. We'll go through it in an example more carefully. But the point is that this exactly captures the co-roots that were labeled in blue from the last couple of slides. And so it makes sense to think about the the generalization to root systems as taking this Sommers region and intersecting it with the co-root lattice. So the co-root lattice, excuse me, is giving you the A, and then the Sommers region is giving you the B. So a non-type A example in our B2 from before. So there's a lot going on in this picture, but we have I've drawn the two, excuse me, the two simple roots in blue. So that would be these two. And then the highest root, which I guess I've changed notations. I called it A tilde before, but now I'm calling it A0 in purple. And just copying the definition of the Sommers region from the previous slide and plugging in the relevant numbers, which are 1 and 1 that come from taking the number 5, which is our B, and dividing it by the Coxeter number. So the quotient is 1, so that's this like pink one, and the remainder is also 1, which is in green. So the green one is sort of the one that tells us the shape of this object. It says that all of the simple roots, the roots at height 1, are going to be, we're going to use those in this like greater than condition. And all of the roots of height 3, that is h minus 1, which in this case is only the highest root, is going to control this like less than condition. And what you are greater than or less than is determined by the quotient. So minus 1 and then 2, which is 1 plus 1. So these are bounding the these are bounding the Sommers region, and in particular, they are these hyperplanes that we had before, except they are sort of moved away from the origin a little bit. So the two that come from the simple roots are shown up there in blue, and then the one that comes from the highest root, the purple root, is shown in purple. And when you go through and carefully check, you can see that yes, the region that you think is between these three is actually what these inequalities define. And in particular, this means that there are 6 simultaneous cores, right? B2, 5 cores. So this is some calculation, and we can sort of keep doing this in general. But I want to remind you of what we were seeing in the type A story, which is that we had that triangle. Let me go back to it. We had this thing that sort of started out as like not really looking like a triangle, but like now that we know that that's what it's going to be, when it gets bigger, it's sort of believable that it would be a triangle back there. And it just sort of keeps getting larger. And this may suggest that we can do things with Ehrhart theory. So I'm going to state this theorem with a lot of undefined terms because, as we'll see very shortly, we're not going to end up using this theorem directly. But this is sort of the dream, which is that if we take a polytope, so in this case, our triangle, and its vertices lie on a lattice, right, like maybe the covert lattice, then we can think about the function that just counts how many lattice points are contained inside scaled versions of that triangle. And that's a function, you can't stop me from defining that function, but what's surprising is that it's a polynomial, and even more than that, you can bound its degree. It's the same degree as the dimension of the So it would be nice to use Ehrhart theory, but we have two problems. The first is that the vertices of this Sommers region don't lie on the points of the coroot lattice. You can see that, for instance, in type B, we have those intersections. For instance, this bottom intersection down here is nowhere near a coroot point, or a point in the coroot lattice. So this seems bad, but it's something that we can overcome because it's not an integer polytope, it's not a lattice polytope, but it is a rational polytope. So there's some scaled version of the Sommers region that does, in fact, have lattice points for vertices. And this makes things a little bit more technical. It means that we have to think about quasi-polynomials instead of polynomials, but you can do it. But maybe a more serious obstruction is that this Sommers region is not actually the dilation of a fixed polytope, which is pretty fundamental for this theorem that at the top of the screen. So the reason why this is because I was showing you b equals 4, b equals 7, b equals 10. But if we switch over to the other residue class, not 1 mod 3, but 2 mod 3, then the orientation of this triangle flips. It was pointing right beforehand, and now it's pointing left. So that seems problematic. But this, it turns out, we can also overcome. There's an explicit element that you can write down that carries the Sommers region to b times the fundamental alcove. Okay, and if the fundamental alcove is not familiar, doesn't matter. The point is that it's a polytope and we're scaling it, right? So it's something where we could plausibly use Ehrhart theory. I've also said that this element WB, this transformation that carries one triangle to the other, is contained inside of this affine Weil group. And all I mean by that is that it's going to take lattice points to other lattice points. We don't have to worry. We don't have to worry about sort of screwing up the lattice when we do this transformation. So we're now sort of in the position that we could use Ehrhart theory. And indeed, this is essentially what was done, excuse me. This essentially was done by Heyman in 1994. He showed that, so he wasn't thinking about the Sommers region, but he was thinking about dilations of the fundamental alcove, and he came up with this very beautiful formula, and it's defined in terms of some nice invariance, indeed even invariance only of the Weil group, and so which carries a little bit less information than the root system. So the exact what exactly this means is not going to be super important for us, but the point is that you really can use Ehrhart theory to sort of count these simultaneous cores. And what we're going to be doing in the back half of the talk, much less than half, is we're going to be talking about a weighted enumeration. So we're not just going to count each vertex, each lattice point once, but we're going to count it with some weight. And this is where our expected values are going to come in. So this was a theorem with sort of a long history, or at least like a lot of people who were thinking about it. So it was originally conjectured by Armstrong in 2011, finally proved by Paul Johnson 4 years later. And in the interim, Stanley and Zanello proved it in the Catalan case. So when B is A+1, and Agarwal proved it in the Fuss-Catalan case before it was finally got in full generality. And the statement is that if you weight each of the coroot points by, well, okay, so that's sort of taking let me just say it in the type A setting, right? If you look at these cores, they're just partitions, and you can ask how many boxes are in the partition. And you want to know, like, what's the average number of boxes? And it turns out that there's this very nice formula for it. So this is the thing that we're going to try to generalize to file groups. But in order to do that, we need to understand what size means for other root systems. Briefly, as sort of a way of getting into that tangentially, I'm going to say what's strange about this expectation. So the 24 in the denominator maybe strikes you as a little strange. And this might be something that you would say, like, oh, maybe this is an artifact of being in type A and it's going to go away eventually. But that's not actually what's going on. This 24 comes from a rather more fundamental place. And this was not observed by Johnson just because he was using different language, but Thiel and Williams noticed this in their original paper, which is that if you phrase everything in the root system context, you can write size, right, the number of boxes in the partition using this weird quadratic form that was defined by McDonald. So that's why his name is in the citation. And the point is that there's this second term that's sitting out there, which is we take the this Weyl vector of the dual root system, something. And that is where this 24 actually comes from when you evaluate that norm. So in 69, Freudenthal and de Vries had this book on, I don't remember like the full scope of the book, but certainly there's a lot of Lie theory in it. Where they give an explicit calculation of this norm, and it turns out that this number 24 shows up there as well. They called it the strange formula, and so when Thiel and Williams were writing their paper, they called this the strange expectation because that 24 just carries directly through into the denominator of the expectation. So this proposition here, we're going to take as our definition of size for general type, because we can write it without making any references to lambda as a partition. So this Weyl vector, this Weyl covector that I sort of skipped over from before can be defined in terms of the co-roots. You just take all of them, all of the positive co-roots, add them together and divide by 2. And that lets you define this thing, where that WB tilde, remember, is this element that converts the Sommers region into the dilates of the fundamental curve. So you might object that size really should not depend on B, right? It should just be a statistic of the core and not like this other parameter. It turns out that, if you go through the exact definition of what WB tilde is, you can get this formula, which doesn't depend on B. And is like sort of easier to work with in calculation. In particular, these two formulas, I say it's easier to work with in calculation, but these two formulas have different advantages. The first one is really thinking about the elements of the dilated fundamental alcove, right? Because we've already applied this transformation to get them there. But the second formula is really thinking about the actual elements of the Sommers region. So long ago, I promised you that I was going to say something about why, like, how this was different from the original paper. So because of McDonald's quadratic form that Thiel and Williams were drawing from, they ended up deciding to use to write things in terms of row, so the half sum of positive roots instead of the half sum of positive co-roots. In type A, you can't tell the difference between these two things because everything has the same length, so everything is a long root. But this, together with some other things, led them to create a different definition of size that only let them complete the calculation when they were thinking about simply laced type, which means that all of the roots have the same size. So they wouldn't have been able to deal with this B2 example, for instance. And this is the improvement from the newer work. So let's do it in type B2. So I've drawn the objects here. The arrows now are the co-roots. And if we look at one of the elements in the Sommers region, we can do an explicit calculation. The half sum of, sorry, this is why I put this in here. The half sum of positive co-roots is going to be 1, 2. You add these things all together, you'll see you get 2, 4. And so if we do this calculation down here, we get we're going to take the inner product of -1, 1 with, looks like -3, -4. And so that's 3 + 4, which is indeed 7. And we repeat the calculation a bunch of times for all of the 6 different simultaneous cores to get an expected value of 5. So completing the calculation means that we're able to understand this number 5 in terms of purely like a product formula, like we were able to do for, or like Johnson was able to do in type A. And it involves a bunch of things, right? A bunch of these numbers that we were talking about earlier. But you can see that, if you cut off the first factor, you sort of are seeing that A - 1 times B - 1, A plus B plus 1, that 24 is still in the denominator. And then when you're dealing with root systems that are not simply laced, then you have to add on this weird factor. And so that number 5, it comes from this, right? You can see the 5 comes from that H plus B plus 1 term, and then everything else ends up canceling. So I have one more slide about some comments on the proof. I'll put it up here, but I think it's probably time for us to draw to a close. Thank you so much for your attention.
All right, thank you. Let's thank the speaker. Does anyone have any questions?
I have a question.
Hmm?
So the number 24 shows up a lot in like number theoretic contexts with modular forms and theta functions and stuff. And I think that also is supposed to have connections with like partition theory and cores and stuff. So I'm wondering if that is maybe why the 24 was showing up in this original like 1969 paper, if you know anything about that.
Yeah. So the so the Freinfeld-Vries result is phrased in terms of like he's interested in trying to calculate the dimension of the semi-simple D algebra that's associated. And so I think that it's in the same chapter as he's talking about the file character formula. Very strong vibes that but I don't know the details myself.
Right. Yeah, thanks.
For sure.
There is a relationship to these McDonald denominator formulas for the affine Lie algebras, which later got generalized. And there he comes up with, if you know, these expansions for I think it's the tau function to certain powers, the Ramanujan tau function. That's a specialization of the McDonald denominator formula, and that has connections. So yeah, that 24 definitely has number theoretic meaning.
Okay, cool, thanks.
So I think for all of the formulas and stuff, you assume that the numbers are coprime. Is there anything you can say when you don't make that assumption, or is that super important?
Yeah, so you certainly can't say very much like enumeratively, because if the even in type A, you can see that if the numbers, if A and B are not coprime, then you're going to get an infinite number of these simultaneous cores. But Johnson was like describes sort of a way of still thinking about these things, and I don't know if there's like, maybe if you throw things into generating functions. I know that Nathan very recently has sent me some generating function results. I don't know if you have more thoughts on that.
I don't know. I mean, if you thought about, lattice paths for non-coprime parameters, then there are formulas that were, that Drew found in that, Journal for Actuarial Science way back when. Bisley formulas as a sum. So maybe the right thing to do, I don't know. Yeah, you might be able to say something, but it wouldn't have such an attractive product form. Maybe it would be a sum of some things. I don't know.
If there aren't other questions to ask while the recording is on, maybe we'll thank the speaker again, turn off the recording, and then ask for secret questions.